Welcome to my talk on taming horizontal instability in merge trees, which is joint work with Florian Wetzels and Christoph Garth. So what's our goal? We want to compare scalar fields. For example, here we have different shapes in different poses, and we want to somehow compare them in a semantically meaningful way, which means that similar shapes should get a small distance, whereas dissimilar shapes should get a large distance in our distance. Okay, but how do we do this? Well, comparing scalar fields directly is really hard. So what we do instead is we compare abstractions of these scalar fields. So we first take our scalar fields and we turn them into some topological abstraction. For example, what we use in the paper is we turn them into a merge tree. And then we compare the merge trees instead of the original domain. And these merge trees, they're much simpler to handle. Typically, in this example here, they only amount to 20 to 30 nodes. So computationally, they're much cheaper than the original scalar field. Okay, but when we do that, we kind of lose a lot of information. And so we need to make sure that our abstraction is still good. And so two properties that we want to have is that the distance on the abstractions should still be discriminative, which means that if the scalar fields are very dissimilar, if there are large changes, then the distance on the abstraction should also show this. So for example, if we have a human shape and a lion shape, there should still be a large distance even on the abstraction. And similarly, we want the distance to be stable, which means that if there's only small changes in the original scalar field, these should only amount to small distances in the abstraction. Okay. Now, if we have this abstraction, so if we have these merge trees, how do we actually compare them? Well, a common technique in computer science is to compare them using a tree edit distance. And I don't want to go into too much detail how these work, but the idea is that they are based on edit operations, such as relabeling a node, deleting a node, or inserting a node. And then we want to find a sequence of edit operations that very cheaply turns one tree into another, and this defines our distance. The cheapest sequence of edit operations gives us our tree edit distance. Okay, but it's not just one tree edit distance. There are actually many different variants based on which edit operations are allowed and so on. For example, there's general tree edit distance, there's the alignment distance. And usually this is kind of a trade-off between the computational complexity of computing the distance and its expressiveness or accuracy. Okay, and we can also kind of plot all of the merge tree edit distances according to their computational complexity. So there are many different merge tree edit distances, and they kind of are either cheap or they're very accurate. And in our paper, we actually focused on one end of the spectrum. We focused on the, tricky one that supposedly should be the most accurate. Okay, so we analyzed this deformation-based edit distance, and it turns out that this is actually NP-complete, which is not too surprising because it's based on the general tree edit distance, which is also NP-complete. However, we still tried to compute it using a reduction to an integer program. And it turns out that with some optimizations, it was actually feasible to compute it up to around 25 nodes. It's still not that good, but it's enough to do some experiments. And it's enough to try to find out, is it even any better? So if we invest this much computational power, do we get something out of it? And turns out this is the case. So this is a correlation matrix for this Tosca ensemble, for these shapes that I showed earlier. And so each of these clusters here is one shape. It's different poses of one shape. The first one here is all cats. And so these should be completely blue. And all of these other clusters should be blue. But in the other edit distances, you can see there's instabilities everywhere. So there's these lines going through the clusters. And in the deformation-based edit distance, turns out it is quite stable. So there are basically no instabilities in this matrix. And in the paper, we also compared this to other techniques to increase stability, such as epsilon preprocessing. And yeah, it's also better than those techniques. Okay, So what are the conclusions? Well, the deformation-based edit distance is hard to compute. It's NP-complete. However, it is feasible to compute it for small trees, and the stability in the experiments is very promising. And so the hope for the future would be that maybe we can take some aspects of it, make them tractable, and also increase the stability of the other edit distances in a more scalable way. Okay, thank you for listening. That's it.